Data Skeptic features interviews with experts on topics related to data science, all through the eye of scientific skepticism.
Marco Tulio Ribeiro is a PhD student at the University of Washington. He has a bachelor's and master's degree in computer science and is currently researching methods for making machine learning more interpretable and trustworthy. To this end, he created LIME, or Locally Interpretable Model-Agnostic Explanations. It is this project that I invited him here to discuss today. Marco, welcome to Data Skeptic.
Oh, thank you. I'm glad to be here.
So I thought maybe it would be useful to start out our discussion from some first principles. Perhaps you could tell me, what is a black box, and what are some of the negative perceptions of the idea of a black box?
So black box is basically, as I understand it, it's a system that does something for you, gives you predictions or performs some behavior, but you don't know how it works. The internals of it are completely hidden from you. In machine learning specifically, we call a lot of models black box, even though we could inspect them. When inspecting them would take so much time that it basically is infeasible. So if you have a really deep neural network making predictions, in theory, you could go and look at each individual neuron and the activations and etc. But it's so large that it's functionally a black box for humans.
So I guess if I'm interacting with a black box, I can, maybe it's even too complex for me to understand. I've opened up a couple small appliances at home and looked at the circuit boards and says, wow, this is beyond what I was taught. But I can at least turn on that device and say, well, I can see it's working, I can test it, and I can maybe even check its accuracy. So is accuracy enough? Should I just trust that the model has had good performance on some training set?
Well, that's a great question. First of all, of course, everyone who does machine learning knows that just looking at error on a training set is a terrible idea, because you can quickly overfit and learn patterns on the training set that will not happen even on a test set or in the real world. So you can be really good at one specific data set, but usually we want machine learning methods to work on other data sets, not the ones we use to train. But even if you do the right thing, in quotes, if you do cross-validation or have a held-out test set or something like that, there's a lot that still could go wrong. There's a lot of problems that can creep in where you overestimate your accuracy. And this is very common. There's been some research that shows that people consistently overestimate their accuracy. In fact, anyone who has ever tried to do a machine learning algorithm and put it into production knows that this is the case. You typically overestimate your accuracy.
How does LIME help us deal with situations where we might have overestimated the accuracy of our models?
So the thing is, humans have a lot of good intuitions about things. If I'm training a model, one of the examples we have in the paper, we're training a model to distinguish between atheism or Christianity emails. I, as a human, have some knowledge of what atheism and Christianity are, so I know what the model should be using and what it shouldn't be using. So if I see an example where the model is predicting that emails are atheism or Christianity, using words that are completely irrelevant to atheism or Christianity, for example, stop words or something in the email headers, I know that something is wrong. Similarly, humans have a lot of intuitions about a lot of things. If I'm training a vision system, I know where things are in the image and I know what the model should be picking up on. So LIME opens the black box, as it were. It explains individual predictions. And from there, humans can use their intuition to have insights, figure out what is wrong, and potentially fix it.
So would you say LIME is an algorithm, or is it a family of algorithms? What's its sort of formal definition?
I think the way we set it in the paper is we set it up as a framework for generating explanations. We did some particular explanations, in particular linear models, but LIME is basically an equation that tries to balance interpretability with faithfulness. So I would say it's a framework. You can derive many different kinds of explanations with the LIME framework. We have been working on many different ones. In the paper, we have a couple of them for images and text.
Very cool. Yeah, I want to get into some of those specifically, but let's maybe take a moment and chat a bit more about that newsgroup example. So if I read it correctly, you've pulled some posts from an atheist newsgroup and from a Christian newsgroup, and then we're going to try and build a classifier that looks at a post it's never seen and decides which group it came from. Is that right?
That's right. This is an old data set. I didn't pull it up, but this is a famous data set that's a benchmark in a lot of machine learning throughout the years.
Yeah, because of course these groups have very significant difference on one thing, but they'll frequently talk about it in the same way. So an atheist, while they might not believe in God, they would use the word God in a discussion of atheism. So I can see the interesting challenges of this problem, and I've seen some people Yeah, I've seen people report really high accurate predictions on it. What are some of the problems that you noticed in looking at other solutions where people try to predict where a new post should go?
Usually when people talk about this data set, they present it as if they're learning the topics. I'm learning how to distinguish between how people talk about Christianity, talk about atheism, and there's other news groups as well. That's how they think. That's what they want their models to do. This particular data set is not very big, and it has lots of extra information, like it has the email headers, for example. The news groups were collected in, I think, 1997 or something. But some news groups have posters, some particular users that post there a lot. So, for example, in the atheism news group, there was a user who's named Keith. His name is present in 12% of all atheism emails. So that becomes very informative. Keith, If you see Keith, you know it's atheism. And by some coincidence, there's no person named Keith posting on the Christianity news group. So right there, you have a perfect predictor. If you see the word Keith, it's always atheism in this particular data set. Likewise, there's a lot of email addresses or institutions where it just happens that in this data set, they're very predictive, but of course you wouldn't expect them to help at all in the real world.
Yeah, that's a great example, the Keith case. It just so happens that there were no Christian posters named Keith. So how would I learn that in the traditional way? If I was going to go inspect a model, what would it take for me to uncover this sort of Keith anomaly?
Well, if you use a model that is interpretable right away, for example, if you use a linear model, you may be able to look at the individual weights. However, the vocabulary is pretty big. And a lot of times, even if you have patterns like this, there are other patterns that are maybe valid. So, for example, most classifiers will learn that the word Christianity is a good indicator for Christianity. So that makes sense. So it's easy to miss this sort of pattern, even if you have an interpretable model. If you have a neural network, or gradient boosted decision trees or something like that, like a random forest, it's really hard to know that the model is picking it up. What you could do is do some exploratory data analysis to find out the most abhorrent examples. So maybe you would find out about Keith. But there are subtler examples as well, both in this data set and in others, that you would definitely miss. And I would argue that it's much easier to see these patterns if you see the model using it. Instead of trying to find it with no model, if you have a model that's using it, extracting it from the model is much easier.
I've noticed a trend towards more complex approaches, especially in text. Things like word encodings have gotten very popular, which make it much more difficult to inspect a model. How can we use Lime to better get us some insight into what the classifier is actually relying on?
So that's right. More and more people are using features that are themselves completely opaque to humans. And I think one of the key ideas that we had in Lime is separating out what the model is using from what a human understands. So we have what we call an interpretable representation that is what we provide the explanations in. So even if the model is using, let's say, word embeddings or something, the explanations are still in terms of words. Now, of course, there's going to be some loss there. We can't perfectly explain what a model is doing unless you have the model itself on the features themselves. But a lot of times you can have a pretty good approximation, especially if it's one individual example. So even if the classifier is using word embeddings, I'll explain it still using regular words.
How do you manage to do that? Let's talk a little bit about the specific use cases then. Say I have, out of my big corpus, I have 10 particular posts that I'm interested in. What are the steps that Lime goes through to give me some insight and hopefully build my trust in the classifier?
It's really simple. The idea is that I'm going to learn another model on top of your model. So we have an example, let's call it X, that we want to explain. What we do is perturb X in different ways, generating a bunch of new data, fake data as it were, perturbed data, and then we get predictions for that data. So for example, if it's a text example, like an email in the news group, we'll remove a bunch of different words every time, and then we'll make predictions. With those predictions, we create a data set. So we have a data set of perturbed examples and predictions, and we learn a simple model on top of that data set in such a way that we care more about perturbed examples that are close to the original one. So if I completely remove every word, I don't care if my explanation captures that case very much because it's so unlike the original example that it's too far. But if I only remove one word, I want the explanation to get that right. Meaning in the explanation, if I say that that word is important, it really is important to the underlying model. So just summarizing, the main idea is we perturb the example in different ways, get predictions, and learn a simple model. And the reason why we would be able to do that is because even really complicated models are not that complicated in a fixed neighborhood. Like around a point, they may be simple.
Makes sense. Could you tell me a little bit more about the advantages you see in the perturbation case? So I could see two approaches. Maybe if I want to train this model on top of the model, I could grab 100 posts at random and retrain a classifier. Or I could train them by this sort of distance metric you guys are using. What advantage does that local choice give me?
One advantage right away is that I don't need access to the training data or anything like that. I only need an instance and a classifier, and I can generate an explanation. For example, I explained predictions from Google's Inception neural network. I didn't even look at their training data or anything. Mm-hmm. Another thing is that when your data has certain regularities, for example, in the 20 newsgroups case, if you sample from that data, you still get that kind of regularity, even if you don't want it. So you may not notice certain patterns if you just use the original data. So you could do potentially a mix of the two, but I think perturbing is really useful to get data that you otherwise wouldn't, to avoid biases in the data set, for example.
I love the idea of helping users develop trust in a model, which is really what drew me to the paper initially. So I was thinking about this newsgroups case. It makes total sense that even if the prediction's correct, if it says we determine this is an atheist post because it was by Keith, I'm going to be very skeptical of that. Do you maybe have any examples in the other direction of things that would give me confidence that the model has correctly classified between, the atheist and the Christian newsgroup?
If you notice that it's picking up, I have noticed when even bad classifiers still learn some useful patterns. Mm-hmm. For example, if you have God with lowercase g, that tends to happen more in atheism newsgroups than in Christian newsgroups. And models pick up on that.
Yeah, that one's interesting. Yeah, I could also see Christians might talk about scripture or mention, Paul on the road to Damascus, while atheists would talk about Dan Dennett or Christopher Hitchens. And
makes sense, yeah.
Yeah, those are things that convince me it knows it's picked up the intuition, I guess.
But that's part of the idea. We as humans have intuition. We know what a good explanation looks like in a lot of cases. And if we see that the model is acting in sensible ways, we tend to trust it more.
Yeah, absolutely. So I've deployed a number of models in my career, and sometimes there's a struggle when you're replacing a function that a person used to do and the model is going to be better at, and the person's a little bit resistant. But I've also had the opposite problem where I deployed a model and I had supporters who were too confident in the results, and they were maybe assigning it strong AI properties, that they found a tricky example that the classifier indeed got correctly, but didn't necessarily get it correct for the most convincing reasons. How might Lime have helped me in that situation?
I don't know if you've heard about the tank example. It's a very common example that machine learning professors always use in their lectures.
Let's go into it.
The story goes, I don't know how true it is, but that someone was developing some contract for the Defense Department or something, where they were trying to identify camouflage tanks. And the model had perfect accuracy, even on validation data. It was perfectly able to identify when tanks were camouflaged or when it was just trees. Mm-hmm. As the story goes, when they tried to apply it in the real world, it completely failed. And the reason was the way they gathered the data was such that either tanks were only present during the day or at night. I don't remember which. But basically, if photos were taken at one time of the day, there were always tanks there. And if they were taken another time, there were no tanks. Now, I'm sure that if the story is true, I'm sure that the developers who first developed the system invented all kinds of explanations for it. They were like, oh, yeah, it's probably detecting the texture in the tank or something like that. It's easy to assign reasons like that when you want your model to work. If you had something like Lime, you'd just see that it's just looking at the background. And we tried to replicate this experiment in our paper. We don't do tanks. We do to differentiate between dogs and wolves, which is supposedly similar. And we asked people, why do you think the neural network is doing this? And lo and behold, they come up with all sorts of reasons. Oh, it's because it's something in the wolf's eyes or the husky's nose. When in fact, we trained the neural network in this particular case to just detect snow in the background.
Yeah, makes sense. So in that respect, are we really talking about a system for double-checking that something hasn't overfit, or is that just one special case of what Lime can help with?
I think that's one special case. Overfit is a problem. Data leaking is another problem. Maybe your feature engineering is not capturing what you wanted to capture, and Lime could help you perceive that. So overfitting is one of the problems that can appear, but even if you're thinking of systems that work, I use the doctor example a lot. If you tell a doctor, look, you have to do surgery, probability 90%, no doctor is going to do anything based on that.
Mm-hmm.
But if you say, look, you have to do surgery, look at this symptom, look at this other symptom, look at this similar case, then it's much more likely that the human decision maker will do something about it. So it's not only for when things aren't working, but it's also for when things are working.
So I know a common problem in machine learning is when you have a class imbalance. Let's maybe pick a classic example like fraud detection. Most of your transactions are good, law-abiding people, and just a few minority bad apples are in there that you're trying to detect. So if I were to randomly sample a bunch of transactions and show someone the outcomes and also use Lime to show them some supporting details of why we think the model arrived at its conclusion, it may be that we sort of deceive ourselves into thinking the model's good because it's covering these average cases but not covering the minority cases. Is there a way you can pick the more interesting examples that might highlight sort of the rough edges of the model?
That's a very good point, and that's something that I'm working on. We did have an initial solution in our paper. We had a system that chooses which examples are going to be shown to the user instead of just doing it randomly. And that's already a start. But for the situation you're mentioning right now where you have big imbalances, or there's another case where you have different costs for making mistakes. So if you're a police officer and you're going to arrest someone based on a machine learning system, you'd better be right. Mm-hmm. So you really care about not getting that wrong. Or spam detection is another case. I haven't seen work, and I haven't done the work myself on selecting instances in that particular kind of case where you have high imbalance or different costs. But it's certainly a very important problem that needs to be addressed.
So I really like some of the visuals you have in the paper around the newsgroup example where, like we keep going back to, if it says, hey, the reason we picked this is because the most prevalent word feature is Keith, that gives me some skepticism, but if it picked it for some other reason, I might grow in trust of the model. So it seems like this is very nice for text. How can this work in other settings, like in the images you were describing?
So for images, what we did in the paper was we highlight the area where the system's using the most to make a prediction, and we make everything else gray. And that's already it's pretty good. Images are easy to interpret because we just look at them and it makes sense. Mm-hmm. There are other representations that we're working on that would give us even more power. For example, if a system is looking at the tone of the image to see if it's grayscale or something, this representation that we chose would not work as explanations. It would not be able to explain this kind of behavior. So it's always a tricky thing trying to figure out what the representation is. You want it to be really interpretable, but at the same time, you want it to be powerful enough to show things. Even in the text case for trained newsgroups, for example, if we just show a sequence of bars, like a bar plot, it's hard to pick up on things such as sequence and things like that. So we are developing visualizations and things like that that are more powerful but still interpretable.
Makes sense. Yeah, I found the graying out approach you guys developed to be pretty effective. In fact, you have a great example in the paper of what I would consider an image that's meant to be sort of deliberately misleading. Could you describe that image and how Lime ended up breaking it down?
Yeah, so we have we have a dog playing guitar, and it's a person's body. So it's a really funny YouTube video of this dog on human clothes, and there's a human playing the guitar, and it looks like the dog is playing it. Of course, the neural network gets that it's very confused by that. And it makes a mistake, actually. It's an acoustic guitar, and it predicts that it's an electric guitar. But it also has high probability for acoustic guitar in Labrador. The particular dog is a Labrador. And at first, I was a bit puzzled as to why it would think it's an electric guitar. But when you see the explanation, there's a part of the acoustic guitar that looks exactly like the electric guitar. So the classifier could have got it right, but I'm not that surprised that it got it wrong. It's not like an egregious mistake. I understand. The acoustic guitar explanation is also pretty good. It shows the part that the acoustic guitar, and the Labrador example just picks up on the dog's face. So obviously this is a confusing example, but even though the model made a mistake, I still trust it because I see that it's doing sensible things.
So let's say I was a user of a particularly complicated model. Maybe I'm a doctor looking at some very complex thing like depression. And I say it's complex in the sense that, if I get a cut on my hand, you stitch it up or you don't. It's pretty straightforward what happens. I think depression has numerous causes, and sometimes it's chemical versus psychological. So it's almost like you need a personalized diagnosis. If I were a doctor and I had access to a model and I was going to use Lime to help me with that diagnosis, what would that user experience be like in a perfect world?
In a perfect world, we would have the doctor see the prediction, like this patient has depression, for example. And then the system would give it all of the evidence in terms of like, look, this patient has depression because look at this particular exam that you did. It would even go as far as saying, look, I would have even more certainty if you did this other exam. It would even mention previous data, like, I think this patient has depression because of this exam. Look at all of these other patients that had a similar result on this exam. It would be more causal even. And that's something we're far from achieving.
Sure. I think everyone in general is.
Yeah.
So when I was very excited by your work, and I was thinking, well, what would be the contrary position? And the first potential for criticism that crossed my mind was to say that every local model you build might essentially just overfit to that local fidelity area. And then it's more like you have this amalgamation of all these local models, which is a lot of degrees of freedom. Could you talk about how you balance between picking those local fidelity models that are faithful to the global classifier, yet particular to the local instances? It seems like there's sort of a trade-off there.
There is a trade-off, and it's a very clear one. If you want something that's interpretable globally, you are restricted to using a simple model. There will always be some approximation error, even when doing this kind of explanation. The nice thing I think about Lime is that you can choose what that trade-off is going to be. So if you really care about being really precise, then you got to put in the time to look at a really long explanation. Also, we can measure how good or how bad the approximation is, even in the local region. So you can imagine if you're using Lime in the real world, sometimes it's saying something like, look, I have this explanation, but I know that it is not 100%. This explanation, you can't really trust even this explanation. So you're going to have to do something else. So kind of like letting you know when I'm failing gracefully. And I think that's helpful. But yeah, it is the case that we are explaining the global model by a bunch of little interpretable models. The nice thing about that, though, is that intuitively that makes sense. Some examples only need a little bit of evidence. Like, let's say I'm trying to predict atheism and Christianity again. If you see a post that has 100 references to Christianity, a lot of Bible verses and etc., it's very easy. So you can find a linear model that approximates it well. If you see a post that's really hard to tell, like if there's some debate going on, then it does make sense that the approximation could be a little less faithful if the model really needs to be more complex.
Interesting, yeah. So perhaps the fact that a post comes from, Reverend Smith, the fact that they have that title is all one needs. But yeah, if they're debating, the ontological argument for God, then it's a little bit more of a gray area or something like that.
Exactly.
Interesting.
And usually in machine learning, we do not want models that are always super complicated because those models tend to be really fickle. Like if the explanation needs every single word, like if you change a little thing, the explanation will be completely different. That means that the model is too jumpy, and we usually don't want that in machine learning anyway. So I think it's a fair assumption.
Yeah, absolutely.
There are cases when it breaks, but it is a fair assumption, I think.
Yeah, that's an excellent point. So trust, which kind of is what I think this really comes back to, the value that I hope to derive from exploring Lime in my own work. Trust is a concept that's a bit fuzzy for machine learning, at least to me. You can't calculate it as easily as you can accuracy or F1 score, or at least I don't know how to. Is it measurable at all?
That's a good question, and I don't know the answer to that. I think there is a sense when you are assigning a binary measure to it every time you put a model into production. If you put the model into production, you trust it to be better than what you had there before. So in that sense, you did trust the model. Whether you should have or not is a different question.
Oh, absolutely. I agree. I actually meant it more from the perspective of a user. So I could show a user two models and ask them, after interacting with both, which one do you trust?
Well, we do an experiment. We don't measure trust by itself. Like I don't know if the users would be willing to pay for something, which would be a way of measuring if they really trusted. In the paper, what we do is we have scenarios where we know you can't trust the model. We try to see if the users can perceive that. It's much more complicated, though, if you want people to actually trust it. If you have a model that's trustworthy and you want people to trust it, I don't know how I would measure that except by having them use it or have to pay for it somehow. It's easy to measure when you can't trust it.
Sure.
Which is what we did in the paper.
Yeah.
We set up models that we know are untrustworthy and saw if people could figure it out.
Well, from my point of view, trust is the complement of untrustworthy, I suppose. Could we talk a little bit more about those results and what you were measuring with your users?
For sure, yeah. We have 3 experiments with users. 2 of them are with non-expert users. There are people in Amazon Mechanical Turk. So we took that classifier that we trained on 20 news groups, the one we've been talking about, that's an untrustworthy classifier. We collected a new data set, a religion data set, that does not have the problems that 20 news group has. We collected web pages. We want to use the model trained on 20 news groups to predict Christianity and atheism in web pages, and we tell users that. We can measure the accuracy of the original classifier, and it's really low. It's like 57%. What we do then is we train a clean version of the classifier. So we clean up 20 news groups. We remove the headers, remove names like Keith and etc. And we measure the accuracy of that one on the hidden set, and it's higher. It's like 69%. We then show users predictions from both classifiers side by side, saying, look, these are the predictions, and these are the reasons. And most times the prediction is the same. They're both predicting the same thing, but for different reasons. So the user sees a few explanations and chooses which one they think is going to generalize better. And this is trying to simulate the scenario that we have very often. When you want to put a model into production, you have a bunch of competitors. They may have different accuracies and they may have similar accuracies, but you want to know which one to trust. And this is an additional thing that you could do, look at the explanations. In our experiments, even non-expert users were able to pick the right one 89% of the time, which is pretty impressive.
Yeah.
If you just looked at accuracy, you would pick the wrong one every time, because using this kind of untrustworthy features increases your accuracy on the validation set. This is the first experiment we did, choosing between classifiers. On the second experiment, we had the users actually interact with the explanation. So when they saw an explanation, they could click on words that they thought shouldn't be used. So if the user sees a prediction for atheism, and in the explanation you have Keith as an explanation, the user can click on that and say, look, the model should not be using this. And we do this several times. And the interesting thing is, even for users who are not experts, they do not know about the hidden data set. They only have knowledge about Christianity and atheism. And I don't even know how much knowledge they have of that. Clicking on words, clicking a few words the average time I think it took was 10 minutes. They could significantly improve a model. The model on average started with 57% accuracy on the hidden set, and in the end it was like 72% or something. And what's perhaps even more interesting is when I did my round of cleaning with no Lime, I was just using regular expressions and stuff, I got lower accuracy than the mechanical Turkers did using Lime. So I guess that says something either about me or about Lime. I hope about Lime.
Yeah, I think that's a really fascinating use case. I've done some experimenting with active learning where I try and pick good examples to have a user label to help me build up a training set. But we're talking about something a little deeper here, where you show a choice a model made, and you're soliciting feedback about the innards, if you will, of the model. Is that the right way to look at it?
It is. And the way that we did it is very rudimentary. The only thing we're doing is removing features. Going forward, I'm very interested in developing more expressive forms of feedback, still not requiring the user to be an expert in machine learning.
Would you consider that sort of a form of regularization, that you're showing the user some of the details and asking them to penalize some of the features?
You can think of it as regularization, but it's not trying to avoid necessarily overfit. You're trying to guide the model to do things that you think are sensible. And this stems from the fact that most of the time in machine learning, we cannot really train or measure what we really care about. We measure accuracy maybe, but what we care about in the end is user satisfaction, for example. Mm-hmm. And we can't really write that down. But humans have a lot of intuitions, and they can know that something's wrong when they see it. So if you could steer a model towards what you want, that would be very helpful.
So I could see where Lime can apply in pretty much any machine learning deployment. I was curious if there are any specific areas or industries that you're most interested in.
Not in particular. I'm interested in, well, obviously in the paper we did more stuff related to NLP and vision. Mm-hmm. Those I think are pretty interesting because it's situations where humans have intuition. I don't know how useful it would be for some crazy genome data. I don't know how much intuition I have about that. I'm not a biologist. Mm-hmm. But in some scenarios where humans do not have intuition, then I don't know how helpful it would be.
Sure.
So mainly for cases where humans have a lot of intuitions, and text and images are two examples where that is really the case.
Yeah, two of my favorites that you mentioned are the medical one, where a doctor doing a diagnosis, and the policing one as well.
Yeah, for sure.
It would be very concerning to me if police blindly acted on some model's prediction, but if there's an auxiliary system giving them some support for why it made a choice, I think that can have a lot of benefit to society.
So that's a great example of what I was mentioned when I was talking about the mismatch. For example, we do not want our models to be racist if you're using them in policing. But how do you define racism? It's hard to define even for humans. How do you write that down for a model? However, you know it when you see it. You know that if a model is telling you to arrest a suspect because he's African American, you know that that's wrong. That's a blatant case, but humans are able to detect even more subtle cases.
For me, Lime is a tool that's going to help us get some trust that the model is basing its choices on intuitively correct features. In the absence of it, we can have cases where operators, people that consume the outputs of models, maybe have too much trust in their model or too little trust, and that we can help close that gap. What do you think are maybe some worst-case scenarios if we didn't have Lime and people had either too much or too little trust?
Well, if you have too much trust, you get problems like thinking your model is going to work really well and then it doesn't. And the consequences could be catastrophic if we're talking about medicine. There's a great example by a guy called Rich Caruana from Microsoft Research, where he was developing a system to detect if a patient is going to, I think, die from pneumonia. And the idea was you'd have the system, you'd predict if the patient is high risk, you'd admit them to the hospital. If they're low risk, you send them home and give them chicken soup, which is the best thing for low-risk patients, apparently. And he had a system that was really good based on a neural network. In the end, he didn't deploy it because a friend of his was using an interpretable model, which was rules, and it learned a very intriguing rule. It said that when people have asthma, their risk from dying from pneumonia lowers. And humans know that that doesn't make any sense. Asthma increases your risk. When they dug into it, it was because patients who were admitted with asthma got treated more aggressively. So in the way that they gathered the data, those patients ended up having lower risk because there was an intervention. But if they put their system into production, that intervention would not happen. They would be sending people home and people would die. So it's a really tricky situation to detect. And if you don't detect it, the consequence could be catastrophic. In the end, they deployed a model that they could inspect really well so that they could avoid this kind of thing.
That's an excellent example, I think. So tell me a little bit more about the open source components of the project.
I'm trying to always keep the code open source. I'm also trying to get this project going where the idea is that you'd add more and more tools to debug machine learning or interact with machine learning. Right now, what we have there is Lime, but I am working on a few more components for understanding machine learning. And it's really easy to use. It's in Python. You can get explanations for most models with a line of code, like maybe 2 lines of code. And it works. It's very general. It works really well with scikit-learn.
Cool. So people working on the Python data science stack should be very familiar. Is the best place to learn more or to give it a try to visit the GitHub page?
That's right. The GitHub page. And I'm sure you have a link in when you release the show or something. Yeah.
Yep. In the show notes, people can find that link. I'll probably tweet it out as well. So people can go take a look at that. Maybe even send a pull request if they get really involved.
Yeah, sounds great. I have had some pull requests and I hope to get more.
Awesome. And so your paper's up on the archive. I'll link to that as well. Is it going to be presented anywhere else in the near future?
Yes. Next week, I'm going to KDD in San Francisco and I'm going to be presenting the paper there.
Very cool. Marco, what's next for you guys in your research and in the development of Lime?
We are working on multiple fronts. In particular, one that we're working on is going beyond classification to things like structured prediction, where models are even more opaque because the output itself is hard to understand sometimes because it's big. The output space is really big. So that's one future direction, going to structured prediction. We are trying to develop the vision part a little more to go beyond just hiding parts of the image. Also, one area that I think is really important is figuring out which kinds of explanations are more useful than others, and depending on the target audience. So it's some HCI work that goes into that. We are developing different kinds of explanations instead of just linear models. It's really hard, but we would like to measure how each kind of explanation impacts different tasks. So for example, if you want to detect overfitting, is it better to have a linear model or to have a different kind of explanation? Mm-hmm. So that's another line of work that we're going. In the future, I hope to tackle the feedback problem as well. So I noticed that something's wrong. I want the model to do something about it, but I don't want to have to be a machine learning expert. And I want to develop that more in the future as well.
Very cool. And what's the best place for people to follow your work?
I guess my personal webpage, I can send you a link as well. I'm always going to be posting stuff there. I do have a blog that I don't post that frequently in. And I hope that I will be able to put everything on the GitHub project as well. So I hope that by the end of my PhD, I have a set of tools that people can use to interact with their models, all open source.
I'll link to your site as well in the show notes so people can follow up there. Well, Marco, thank you so much for coming on the show to share the story of Lime and your work. I think this is really interesting, and I'm glad it's part of the machine learning conversation.
Well, thank you so much for inviting me. It's great.
For more on this episode, visit dataskeptic.com. If you enjoyed the show, please give us a review on